of e to the x, we want to set up e as a definition. And because it's a definition, you don't have to prove it. E is the limit as h approaches 0 from the right of 1 plus h to the 1 over h power. Now, if you think about that, I don't want you just to say, okay, that's it, I'm going. I want us to think about this real quick, what this means. As h is approaching 0, what is this becoming right here? 1 plus h.
As h approaches 0.
1, yeah. It's getting really, really close to 1. Now, you start thinking about that, well, what is 1 to any power? It's 1. So we're like, okay, well, why would that be e and not 1? Well, now you consider
That's getting closer to 0, so it's going to be 1 over 0 is going to be approaching infinity.
yeah, this is going to get infinitely large, or this is getting infinitely close to 1. It never does quite equal to 1, it just gets really close to 1. And the closer this gets to 1, well, the larger and larger that's getting. So it rounds out to be at approximately 2.72. That's the approximate value of e. So, by definition, this is what e is, but we want to know the derivative. Well, we've got to go back to that limit definition. So it's the limit as h approaches 0 of e to the x plus h minus e to the x over h. That's f of x plus h minus f of x over h. Remember, that was the limit definition of the derivative. Are we okay to keep going? All right. So now, this is equal to the limit as h approaches 0. Now, what do we get if we're adding exponents? What does that mean happened? What had to happen to allow us to be able to add exponents?
Like multiplication.
Multiplication with, like,
Terms.
bases maybe?
Bases, yeah.
Okay, like bases. So this is the same thing as e to the x times e to the h minus e to the x over h.
Oh, that's pretty groovy.
I got the, well said, well said. This is groovy. Now, what happens here? In the numerator, we have an e to the x in common, right? So I'm going to factor out the e to the x, and we're going to be left with e to the h minus 1 over h. And of course, you know, e to the 0 is 1, 1 minus 1 is 0, 0 over 0. So we're still in a form of 0 over 0. So I'm going to pull this out here, e to the x, because the limit as h approaches 0 of e to the x is just e to the x. So I'm going to get it out of the way. This is not necessary, but it helps me stay a little bit better organized. But now I'm going to use this definition of what e is. We've already got it set up as a limit. So e is 1 plus h to the 1 over h power, and then all of that is raised to the h power minus 1 over h. I'm going to slow down because that's going to take you a second probably to copy that down.
So wait, why did we take the? I mean, I know why, like, but I don't understand how we did the. We factored out the e of x.
Yes, e to the x.
Why did we like put it over to the side? Like, what happened?
Well, because this is not relevant to all of this because it doesn't have an h in common, or there's no h to be approaching 0. I didn't have to. I could have left it in there.
Okay. So if it like was in there, it doesn't matter because it doesn't have an h.
Yes,
Okay.
there is no h to approach 0. All right, now, think about your rules with exponents. We've got this exponent here raised to this exponent here, right? What do you do when you have an exponent raised to an exponent? You multiply that out, right. So what is 1 over h times h? 1. So I've got e to the x times the limit as h approaches 0 of 1 plus h to the first power minus 1 over h. So what happens in the numerator? The ones cancel out, right? So we're left with h over h, which is, well, it says it's approaching 0. It's not quite 0. It's approaching 0, so it's
1.
So we get e to the x times 1, which is just.
E to the x.
So what we're saying here is that the derivative of e to the x is e to the x. E to the x is its own derivative,
How does that work?
like
I
this.
mean, yeah.
This is how it works.
So like, is that an exception, or is that like something that can happen like with a lot of different stuff?
There's only one other case right now I can think of where an equation is its own derivative, and that would be f of x equals 0. There may be another case, I just don't know it. Yes?
Like a quiz or a test where we need to like write all this.
No, this is, we have verified this. We don't do this no more.
Would it not work for log as well, since e is just the inverse of log?
We're gonna do log. But no, it's not itself. All right. So, what that means is if you think about what the graph of e to the x looks like, it crosses here at 0, 1, or 1, 0, I'm sorry. No, 0, 1, I was right the first time. Crosses here at 0, 1. Well, what this is saying is that whatever the y value is on that graph, that's also, whatever the y value is on this graph, that's also the slope at that point. So at this point 0, 1, we have a slope of 1. These points out here, someone do e squared. What is that approximately as a decimal?
Uh, 7.338.
7.4?
7.389.
Okay, so that means that the slope, that is also the y value right here, but it's also the slope. At that point, when x is 2, we have a slope of 7.38 as well. These slopes right here are really small, right? Well, what would like e to the negative third equal?
Really small.
0 point what? 0.09. So we have a very tiny slope right there. But look, I mean, it's decreasing. I mean, well, it's increasing coming left to right, but the slope is very tiny. So that's what we get there. So e to the x is its own derivative. Now, I'm going to use some notation here that I have not used in this class, but I ended up, I usually don't show it till later on, but I showed it to a student yesterday, and that student said that it made it click for them. If we take the derivative with respect to x, that's written as d dx. We take the derivative with respect to x of e raised to the u power. The answer is e to the u power times the derivative of u. So, if y equals e to the 5x squared power, then y prime is going to be e to the 5x squared power, and then times, what's the derivative of 5x squared? 10x. So I'm going to say it's 10x times e to the 5x squared power. We typically write these problems out, letting our exponential function be the last thing there. So are we okay with that? Okay. So what would y equals e to the tangent of x equal to?
So that would just be
Secant squared x times e to the tangent.
Very good. The derivative of tangent of x is secant squared x, right? And it's times e to the tangent of x. All right, we're about to apply, as we called it, the two chains rule. I know it. Y equals the tangent of e to the x squared. Now, you don't have to put it in parentheses, but I will for the sake of this problem. Okay, well, what do we start off with? What is the, and we just did tangent a second ago. What is the derivative of tangent of an angle?
Secant squared.
Yep. Secant squared of that angle, so I wrote tangent, which makes a whole lot of sense. Secant squared of that angle, and then times, times the derivative of the angle, right? So this is a chain rule here inside of this chain rule here. So it's 2x times e to the x squared. Remember, it's e to that power times the derivative of that power. Take a second to let that sink in.
So, like, wouldn't you have to do the power rule to the x squared and then do the power rule to the e? Is that like,
Well, okay, I did it in a different order from what I did over there. It's the derivative of e to the x squared is e to the x squared, and then times that derivative of that angle. So what is that derivative of that angle?
2x?
It's 2x.
Oh, okay.
So I just
Okay,
wrote it
okay,
in
okay,
opposite
okay.
order.
So it's X.
And then 2 would be the,
No, you don't have to take that derivative again.
oh, okay.
Yeah, and that is a frequently asked question. How do we know when to stop?
Yeah.
I said, and I always say, stop when you get to the right answer. That's kind of I also tell people only to second guess themselves if they're incorrect. But
But actually, how do you know when to stop?
this is the correct answer, so I'm gonna stop there. No, once you take the derivative of that angle,
You don't need to keep on.
you don't have to keep doing it. It's just the derivative of secant of the angle, then times the derivative of the angle, and the derivative of the angle is just e to that thing, and then times the derivative of that angle. So you wouldn't take the derivative of that angle, or this 2x, x squared, I'm sorry, get 2x, and then say, and then I need to take the derivative there. You just don't do that.
Can you simplify that?
Well, if I were turning this in, I would say it's kind of different. I'm gonna put the secant squared last, so it's gonna be 2x e to the x squared times the secant squared of e to the x squared. So I mean, that's not really simplified as much as it is just the different order. Can I erase this? Okay.